The next few things I wanted to talk about in regards to the ideal gas law are when we have certain constants or constraints on the system. There are three cases that we'll really be talking about. Well, technically four. The first case, though, doesn't have any special name. It's what we would call or consider a closed system. So closed systems would refer to when the mole count is a constant. So N is constant. So in this case, you could think of PV equals nRT as the before and after of a system. Like maybe I change the pressure. How does that affect the temperature or the volume? Maybe I increase the pressure or I decrease the volume. And I can do that under a certain amount of conditions. But the mole count stays the same. So it'd be closed in terms of the system. So in this case, we would have the before. Kind of think back to our momentum days where we said the before equals the after. After. You can have the same setup here. This would be like P1, V1, N1, R1, but R is always constant, T1. And this is going to equal P2, V2, or it will compare, it won't equal, N2, RT2. But if N and R are always constant, I'm going to solve the equation for N and R. So NR is going to equal P1 V1 over T1. And in the after scenario, or the after case, it'd be NR equals P2 V2 T2. I can set these two systems equal to each other. So this is the case for a closed system. The pressure before anything changes, the volume before anything changes, divided by the temperature before anything changes. That ratio or relationship has to equal the pressure after, the volume after, and the temperature after. So this is a relationship that holds true. So that's going to be the first case that we're going to look at. Now, all of the rest of the conditions we're going to look at are under the distinction that they are also within a closed system. So N is being conserved and it is constant the whole time. So in the next case of what we're going to look at a system that's called isobaric. So this would be an isobaric closed system. N is still being conserved. R is just the ideal gas constant. It's never changing. But the isobaric is under constant pressure. So constant pressure. So in this case, instead of solving for, so I have PV equals nRT, instead of just solving for N and R, I'm going to solve for NR and P. So in this case, I would divide the N and the R, I get P over NR equals T over V. And the same relationship can hold true for this. The before equals the after. So this would be the temperature before divided by the volume before has to equal the temperature after divided by the volume after. And I see that from this, if I just take the pressure term, if it's the same, I'm dividing it from both cases, I still have that relationship. And the same is true if I had the volume divided by the temperature. So their reciprocals are also true. So the volume of 1 over the temperature of 1 is equal to the volume of 2 over the temperature of 2, so long as the directions are in the same. The next one we're going to look at is isothermal. This is constant temperature. So under the PV equals nRT, we're solving for nRT. So it's the pressure before times the volume. So the before case, pressure before, volume before equals pressure after, volume after. And that one's fairly standard. The last one we're going to look at is called isochloric. Don't ask me where the term chloric comes from. Maybe it's a Latin root word, but you could probably guess it's going to be constant volume because that's the only one left we haven't looked at. Isochloric. I think that's spelled right. Constant volume. This would be PV equals nRT, but again, in this case, I'm solving for the volume. The temperature of the first one divided by the pressure of the first one is equal to the temperature of the second one divided by the pressure of the second one. Or because I could take both the reciprocals and compare them that way. The pressure of the first one divided by the temperature of the first one is equal to the temperature of the second one divided by the temperature, or the pressure, sorry. Goodness, I can't do that in the right way. The pressure of the second one divided by the temperature of the second one. So these are the three cases, all as well being considered in under closed circumstances or closed conditions, where we can study ideal gases and how they relate in nature, in closed scientific settings, and it can tell us a lot about a system.